Good morning, and as we continue working in our geometry lessons, we are going to move into right triangle relationships and trigonometry. And the first lesson that we are going to cover here is going to be triangle classification, or is going to be the triangle classification theorem. And I guess moving into these classifications, we probably want to flash back to maybe eighth grade, where we started talking about the Pythagorean theorem. And we learned that in the Pythagorean theorem that we could find the side lengths of a right triangle, and it usually consisted of something where we had A was one leg, B was another leg, and then C was my hypotenuse. And with a right triangle, it allowed us to find these lengths, and the formula for the Pythagorean theorem was A squared plus B squared equals C squared. And we use this over and over again in math in all different variations and refer back to it. So as we look at that, we need to remember that that's what we were using back in the early part of math or in algebra, because we're going to use it now in geometry, and we're going to examine its relationship. So in this triangle classification theorem, we want to know, how can the side lengths of a triangle be used to classify it? Well, we're going to talk about different types of triangles, and of course here we have the side lengths of triangle ABC satisfy the relationship in the Pythagorean theorem. And so again, it's A squared plus B squared equals C squared. It's right here. And because it is a right triangle, and this is a little bit a right triangle, we know that the Pythagorean theorem holds true, because you would have A squared plus B squared equals C squared. And if we look here, in this case, C is going to be the value of n, so it would be A squared plus B squared would equal n squared, because they're both right triangles, and the theorem would be able to be used back and forth. Now, the converse of the Pythagorean theorem, of course, is if the square of one side of a triangle is equal to the sum of the squares of the other two sides, then the triangle is a right triangle. Think about it. The square of one side is equal to the sum of the squares of the other two sides, is what they're asking you. Then we would have a right triangle. So if this holds true, then that proves that we have a right triangle. And in doing so, let's see here, it says, of course, C is going to be our hypotenuse, or our longest side. And then it's always by itself, and it's one side of the equal sign. So as you can see, did it matter which side? We had C squared over here, we had C squared over here. The equal sign allows us to move back and forth, flip it back and forth. So looking here, we have if A squared plus B squared equals C squared, then we can say that the triangle is a right triangle. Again, it allows us to prove that, same information. So as we go to apply that, let's see here, applying this, do we have right triangles or do we not have right triangles? So if we look at example 1, we do some substitution. I know that this is going to be my longest side, so that would be C. I could call this one A and this one B. So I end up with A squared plus B squared equals C squared. So A is 3. Do the substitution. So I have A squared plus B squared is going to equal C squared. And I know that from experience, and some of you may say, well, that's 3, 4, 5. That is a Pythagorean triple. But we will just continue to do the math just to show it. So I have 9 plus 16 is equal to 25, or 25 is equal to 25. And sure enough, that's a true statement, and that would prove that we do have a right triangle, because the square of one side is equal to the sum of the squares of the other side. So yes, we do have a right triangle. Now, our other example 2, of course, we still have our longest side. Then we have A and B. Doesn't matter which A and B are interchangeable. And let's see here. So we would have, again, a squared plus b squared equals c squared. Do my substitution for a, do my substitution for b, and my substitution for c. And this one's, ooh, let's see, I have 10 squared is going to be 100. I have 9 squared is going to be 81, and I have 4 squared, which is going to be 16. So that's 97 is equal to 100, and that is not true, right? That is not true. So then if that is not a true statement, then this is not a right triangle, because the sum of one side does not equal the sum of the other two sides, or the square of one side does not equal the sum of the square of the other two sides. So not a right triangle. So as we move on, we find that if we don't have a right triangle, we're either going to have possibly an obtuse triangle or an acute triangle. So looking here at the side lengths, that will help us make that determination. So if the square of the length of the longest side, right, so we have the longest side of a triangle is less than the sum of the squares of the lengths of the other two sides, then that triangle is going to be an acute triangle. So the square of the longest side is going to be less than the square, the sum of the square of the other two sides. So here we have an acute triangle. Acute triangle is a triangle that has all interior angles that are going to be less than 90 degrees. That would be the identifier for an acute triangle, and of course and then this will help us identify that acute triangle mathematically. So as I look here, or just by the lengths of the side, should I say, not the angles. So if I look here, I have C, I have A, and I have B. So A squared plus B squared and C squared. So A squared is going to be 3 squared plus B squared is 3 squared, and C squared is 4 squared. So I have 16. I have 9 plus 9, and this is going to be 18 and 16. And just looking at that, I left out my symbol here intentionally because I didn't know what was going to happen. And sure enough, the sum of the squares of the other two sides is going to be 18, which is going to be greater than 16. So there you go. This is, in this case, we have an acute triangle. And then if I needed to flip it around like that, of course, 16 is going to be less than 18. So there we go. We have an acute triangle based on its side lengths. And if we have an obtuse triangle now, that will place it into a little bit different category. So if the square of the length of the longest side of the triangle, so if your square of the length of the longest side of the triangle is going to be greater than the sum of the squares of the lengths of the other two sides, then the triangle is we're going to go with a obtuse triangle. So what they're saying here is, if the square of the longest side of the triangle is greater than the sum of the square of the other two sides, then we will have an obtuse triangle. This would, if C squared is greater than A squared plus B squared, then we have an obtuse triangle. So an obtuse triangle is going to be the obtuse triangle is a triangle that has one interior angle that is greater than 90 degrees. So this angle right here appears to be greater than 90 degrees. And if I were to test that, of course, I do have C squared, and then I have A squared plus B squared. So this should be C because it's my longest side. Then I have B and A. So I have 8 squared, and then I have A squared, which is 3 squared plus B squared. And then I have 64, and then 9 plus 49, and this is going to be 58 and 64. And sure enough, 64 is greater than 58. So right here, c squared is greater than the sum of the other two sides squared, and there you have a obtuse triangle. And looking at an example here, so Jax is setting up an obstacle course for his campers in the shape of a triangle, and the distance from the first to second obstacle is 60 feet. Okay, and then from the second to the third obstacle is also 60 feet. How far can he place the third obstacle for the first from the first obstacle so that the course is a obtuse triangle? Let's see, let's draw that real quick. So we're just going to say that we have our first obstacle, and then it is going to be 60 feet from our second obstacle. And the second obstacle is going to be 60 feet, right, from the third obstacle. So we have this distance right here that we want it to be an obtuse triangle. And obtuse means that this angle right here is going to be greater than 90 degrees. And then we learned too, just a second ago as we were talking through our examples, that an obtuse triangle, c squared, is going to be greater than a squared plus b squared. So in this case, we have this unknown value right here, and that would be c. We have b, we have an a, so I could say that c squared is greater than a is going to be 60 squared plus b 60 squared. So c squared is going to be greater than, what is that, 3,600 plus 3,600, or c squared is going to be greater than 7,200. And if we were to put that into the calculator, it would come down to finding the square root of both sides, and c would be equal to approximately 84.85, or should I say not equal to. In order for it to be an obtuse triangle, c is going to have to be greater than 84.85 in order to create an obtuse triangle. And let's see here. So we're looking at, because these lengths are the same, they have to have the same base measure. Goodness, what do you think about that? Skipping back up to that question, what do we know if we're looking at this real quick? Something I didn't identify is if I have an isosceles triangle, and because this length is equal to this length, this angle is equal to this angle, so the angles have the same base measure because we have an obtuse triangle, and then c would have to be that. So the distance between the first and the third obstacles needs to be greater than 84.85 feet. If it equals, right, in order to be obtuse, if it were to be a right triangle, c would have had to equal 84.85, and if it was going to be an acute triangle, c would have had to been less than 84.85. So those are just some additions that we could have looked at. So as we look here at a couple more examples that we'll go over in class also, but I want to find the value of x here on example number 6. Okay, example number 6, and it says round to the nearest tenth. So let me see here. Looking at this, I do have a right triangle. So I should be able to use the Pythagorean Theorem to find this missing side. And if I have the Pythagorean Theorem, so I could go with a squared plus b squared equals c squared. This x I could say is a or b. 16 is going to be a or b, and then my longest side would be c. So possibly have 16 squared plus b squared is going to be equal to 27 squared. going to have to get the calculator out for this one, but I do know that b squared is going to remain the same. And 27 squared is going to be 729, and then 16 squared is going to be 256. Continue solving for b, and I will go ahead and isolate my variable by doing my inverse operations. And so this will become 0, and I will have b squared is equal to, let's see, 3, borrow the 1. I mean, I hope we end up with, wrong button, 473. Find the square root, because we're still trying to isolate b. We're not trying to find b squared. We're trying to find the length of b. So finding the square root. So if we were to find the square root of 473, it would be b is approximately equal to 21.748, and we keep going. If I were to round that would to the nearest tenth, that would be b is approximately 21.7 is going to be b, approximately 21.7. And that's how I would use the Pythagorean theorem to find the side length. We can use another example here, and I'm going to use in the next example, we are going to use right here, we are going to use the Pythagorean theorem to find a side length, but it turns out that the side length we're looking for is going to be our hypotenuse, because it is the longest side and it is across from the right angle. So if I have an a and a b, I would have 12.8 squared plus 5.3 squared is going to be equal to c squared. And I'm going to have to put those in the calculator. So 12.8 squared is going to be, let's see here, 163.84 plus 5.3 squared is going to be equal to 28.09. And then when I add those two together, why waste my time doing it the old-fashioned way? I got a calculator right here. So 191.93 is going to be equal to c squared. Now if I go ahead and find the square root of both sides, would give me the value of c is going to be approximately 13.853, and it will continue on, but we will round that to approximately 13.9, because that 5 will round the 8 up to a 9. So there you go. C is approximately 13.9. Let's see here. We have another example of, given the side lengths, determine whether the triangle is acute, right, or obtuse, or not a triangle. Not a triangle is probably going to go into our investigation in a different question, but knowing these are my side lengths of a triangle over here, I would have 15 as one side, 16 is another, and 21 is another. I should know that C is going to be the longest side, and 21 seems to be the longest side, and then I'm going to have an A and B. And then to find out if it is acute, right, or obtuse, I need to take the longest side squared and see how it compares to the other two sides squared. So 21 squared, and then I have 15 squared and plus 16 squared. And we figured out this is 256 plus 15 squared is 225, and then 21 squared, I hate that I just put that in the calculator, is going to be 441. So 441, and then these two add up right here to 481. So the sum of the other two sides, the smaller two sides, the squares of the smaller two sides, is greater than the longest side squared, which makes it an acute triangle. We have an acute triangle. So we were able to just plug that information in here and find out if it was going to be acute, right, or obtuse. And then the next example, example number 9 here, it says, reads, Kurt is building a rectangular deck. If the dimensions of the deck are 10 feet by 23 feet, what is the length of the diagonal of the deck? And draw a picture and solve. So I have a deck, it's a rectangle. Rectangles, I know that all my angles are 90 degrees, and the dimensions are 10 by 23, and it is asking me what is the length of the diagonal. That's my unknown, and hopefully we can say that that's my longest side across from the right triangle, so that's going to be C. This would possibly be A, this would be B, so I would have A squared plus B squared is equal to C squared. I'm using the Pythagorean theorem because we know that it is a right triangle, so we're using the equal sign. And I would have, goodness, 10 squared plus 23 squared is equal to C squared. So we have 100 plus 23 squared is going to give me a, 529 is equal to C squared. So I have 629 is equal to C squared. Find the square root of both sides. And C is going to be equal to, let's see, the square root of 629 is equal to 25.0798, and it keeps going, so we will round. So C is going to be approximately 25.1, rounding to the nearest tenth. 25.1, and it doesn't, feet. There we go, 25.1 feet. So those are my examples as we talk about the using the Pythagorean to help us to classify our triangles. And again, we have if A squared plus B squared is greater than C squared, that becomes an acute triangle. If we have A squared plus B squared is less than C squared, that's obtuse, because that hypotenuse is overpowering the legs. And then if we have A squared plus B squared is equal to C squared, then we have a right triangle. We have a right triangle. And that's how we were able to use our legs and sides to determine the classification of a triangle.